Sean Christopherson. I'm from Intel. Going to talk about Intel SGX Virtualization. A little bit about myself before I get going. Software engineer at Intel, primarily working on KVM. I sadly do not have a fancy title at this time. I've been working on x86 low-level stuff for about 14 years, and VMX specifically for about 10 years. I did a random instruction test tool for pretty much all Intel ISA for about little under a decade. And I've been working on SGX itself for about 2+ years. Been working on Linux for about 2 years, and working on KVM for a little under a year and a half. So if you want esoteric x86 knowledge, I'm your guy. Virtualization, not so much. Actually using VMX, the hardware capabilities, to do something useful, not quite there yet. So if you're ever get to a point where you're wondering, what am I doing? Or what's he thinking? It's probably just ignorance. So what is SGX trying to do? In the traditional virtual machine landscape, where you've got your attack surface that you have secrets in your application out in ring 3 that are accessible by any privileged entity. So your VMM, your hypervisor, your OS, hardware, firmware, or any malicious app that manages to escape some privilege levels, exploit some flaws to get there. And even in this traditional landscape, if you encrypt your VM, so like MKTME or SME, even SEV, SEVS, it doesn't necessarily take the operating system or the VMM out of the TCP. Same with firmware. A lot of the firmware pieces can still get access to your application secrets. And that's not a knock necessarily on things like total memory encryption of your VM. They still definitely have their place. SGX isn't necessarily, it's not going to replace those. It's not completely orthogonal, but they do have different applications. The kind of main goal of SGX is to reduce the attack surface. So shrink it down to just your application and some of the hardware and firmware. The idea being, even if you manage to subvert the VMM or the OS or even BIOS, you can still have some protections and still protect your secrets from leaking or from attack. The other big piece of SGX that I'm actually not really going to touch on at all today, but it is worth mentioning because it's a large part of the architecture, is attestation. So SGX has a root of trust in the hardware, and this means that it can attest, your application can attest itself to a third party with that hardware root of trust. And that attestation includes information about what's running in the enclave, what the execution environment is. So this is like the hardware execution environment, the CPU's security properties. So whether the Enclave is protected from replay attacks, what type of integrity guarantees it can provide, et cetera. And lots of other stuff that get included in that attestation report. The kind of high-level view of what an enclave looks like starts with a standard user space process. So you have your data, you have your code, and then you have the OS bits that are exposed to user space. An enclave is a trusted execution piece that's embedded in that ring 3 process. So enclaves run in a kind of special new architectural ring 3 only mode. They have controlled entry points, so you can't just jump into this enclave willy-nilly and try and do execution attacks by executing code you're not supposed to. So you can only enter this code at points that the enclave has specifically allowed entry at. Enclaves support multi-threading. It's a little, not cumbersome, it's complex to set up and get working correctly, but it is supported via things called thread control structures. So kind of within that enclave and its protected memory, the CPU stores information about where that thread was running, all of its relevant state, and that allows you to run multiple threads within a single enclave. An enclave has read-write access to its kind of owning process virtual memory. So it's not like a full page table switch when you're going over to an enclave. You still have access to everything that you had access into your user process. So in terms of if you want to rewrite to the exterior world, you can get back to your user process. The exception here is that you cannot execute outside of the enclave. So once you're in the enclave, to prevent an attack or a buggy enclave from exposing itself, if you ever try to execute outside that, so you jump to code that's not in the enclave, you'll get a general protection fault. But it doesn't work the other way around. So the user process, the operating system, can't peek into the enclave. And it's not just memory encryption. I'll get into that a little bit later. The user process can't see anything into the enclave. Starting at the kind of hardware level, there's what's called processor reserve memory. And this is in the hardware implementation for SGX, not necessarily the more hardware agnostic architecture. But realistically, what you're going to see in practice is this chunk, and it's carved out by a range register. And so within that PRM, there's what's called the Enclave page cache. And the Enclave page cache is essentially what's usable for building enclaves. So it's just kind of specialized memory that user space actually gets to use to build these enclaves. And then there's the EPC map. And the EPC map is not exposed to software. It's managed purely by the hardware. And it exists so that hardware has a place to store bits and metadata about enclaves, to do a lot of tracking, to implement the various enforcements with SGX. Bumping one level up into kernel space, SGX exposes a variety of instructions. They're all under one opcode, Enclaves, with a bunch of leafs for implementing various capabilities. So you can create an enclave, add pages to it, initialize the enclave. Then at this level is where you manage all of that EPC memory. So the kernel still has full control over the EPC, as in normal memory. So it can, there's mechanisms to evict pages from the EPC, so do page out and page those back in. And the existing I32 page tables also are in play here. So all of your normal memory management that you do through page tables still exists with SGX. So part of the SGX module in Linux is configuring the page tables for access to the EPC. At the user space level, there's another instruction, Qemu in this case, that has a collection of leafs. And this is where the untrusted portion of the user space process that wants to run an enclave can do things like enter into the enclave, resume a running enclave after it exited for an interrupt. And then on the enclave side, there's instructions that are runnable only within an enclave. So things like exit, an explicit synchronous exit. There's some reporting stuff for attestation, et cetera. For access control, start out with a normal virtual address. Go through the page tables like normal, assuming everything works out with the page tables. So all the normal permission restrictions exist here. All the normal faults for existing I32 page tables are in play. Assuming those check out, we get to a point where we have a physical address in the CPU. At that time, we check whether or not it's an enclave access. And this doesn't mean only accesses from within an enclave. And in fact, because you can access memory outside of the enclave, even accesses that originated from an enclave may not be considered an enclave access. Rather, an enclave access is something that falls into the virtual range of that enclave. So when you create an enclave, the processor, part of the information that's provided is a base and size of that enclave. And so the enclave, when you're running that mode, the CPU keeps track of what enclave it's running, and as well as once it's running, what the linear address or virtual address in Linux terms, what that range of is the enclave. So if an access falls within that range, it's considered an enclave access. And then there are a variety of the Uncle U and Uncle S instructions that explicitly access the EPC, and then those are also considered enclave accesses. If it's not an enclave access, so this is just a normal memory access, we're going to check the range registers, see if it hits the EPC. If it doesn't hit the EPC, it's allowed normal memory access. If it does, and in this case, it's not supposed to be accessing that, we get redirected to the abort page. Abort page behavior is not a faulting case. Abort page, if you try to write to the abort page, it just gets dropped, and then loads return all ones. So the access gets allowed through, but you get junk data back, and if you try to write to it, it just gets dropped. If this was an enclave access, we again check whether or not we hit the EPC. Because these are supposed to hit the EPC, if they don't, you get a fault. If they do hit the EPC, so this looks like a correct access, there are additional checks made. So this is where we go to the EPC map. And this is the hardware managed portion that's not visible to software that does additional checks. So this prevents the kernel or VMM from trying to attack the enclave by changing page permissions or trying to do remap attacks. And so the EPCM enforces the permissions desired by the enclave. If the EPCM is happy, we allow the access. If it's not so happy, then we're going to get that fault again. One weird thing to note with the EPCM faults, the exact fault you're going to get depends on which hardware you have. Early iterations of SGX deliver GP faults, and then it's marked as an errata. The SDM will tell you that you get a page fault with an SGX-specific bit set. On bare metal, the PRM is carved out of RAM with range registers. This is statically partitioned, so it's not something that you can change on the fly. It has to be locked at boot. So similar to like the feature control MSR, the PR MRRs have to be locked. Because they're range registers, this means it has to be power of few sized and naturally aligned. So you can't do like page granularity sizing. Within that PRM, again, part of that is given over to the EPC map. So for instance, on Skylake hardware, the largest PRM size you can configure is 128 megs. But what you actually see for software is only 92 megs of EPC, because the rest of that chunk is to the EPC map for doing all that metadata tracking. The PRM is encrypted with an ephemeral key, and this is a single key that is generated randomly at boot. So it's a per CPU key, and it's thrown away every time we reset. And one thing to note here is that enclaves are not isolated from each other through encryption. It's a single key for the EPC, regardless of which enclave you're running. Enclaves themselves are isolated through all of the other hardware checks, the range checks, similar things coming in through the IOMU, things like that. So the encryption is kind of a defense in depth mechanism, not the primary way of protecting the EPC. From software's perspective, when you're accessing the EPC legitimately, it's transparently decrypted or encrypted when you're reading and writing from DRAM. So it's unencrypted in the CPU cache. And that's all levels of the CPU cache that it's unencrypted. This means that if you can keep your workload within the cache, you're going to see basically native speeds. As long as you can stay within the enclave, keep running out of the cache, you're not going to see any performance hits. And even if you're going out to EPC, which is effectively main memory, plus the encryption, it's not going to be a massive performance difference. Again, that key is generated at CPU reset. This has some unfortunate side effects. This means if the CPU power is down, so we go into S3, or you just restart your machine, the EPC and the EPC map go away. And that has noticeable side effects because the EPC map, if you remember back to the access permissions, does checks on the page permissions. So if you lose your EPC map, suddenly all of your accesses start faulting. And part of the SGX architecture states that this is expected, it's going to happen. And if you are developing an enclave, you have to prepare for it. So user space processes that run enclaves are designed to detect these faults and restart their enclaves when necessary. From a VM perspective, we don't have the same restrictions. We're not limited to range registers. We don't have to deal with the PRM. We don't have the EPCM because that's just sitting below us in hardware. So we can do 4K, standard page size, page aligned. We don't have to overlay it on top of guest RAM. It can be something completely separate. That EPCM behavior, where hardware will blast away the EPCM and suddenly everything starts faulting, can be exploited by the VMM to kind of support certain features. Migration, live migration being the big one. So because the key is per CPU and it's ephemeral, it's generated at reset, migration as is today is not supported of the EPC. But because software is conditioned to respond gracefully to faults to the EPC being lost, on live migration, we can just migrate the page tables as normal, but when you get to your destination, everything starts faulting, but user space doesn't care. They just think that we went into a suspend state or something. You can also do kind of a pseudo reclaim. I'll get into this a little bit later. Pseudo in this sense, because it's really a facsimile of reclaim. You can temporarily reclaim pages. Again, user space in the guest could fault, but at some point, if you want to keep running the guest, you need to give those back in a timely fashion. And possibly other tricks down the road. So non-virtualization page out. EPC is very limited, especially on current processors. So what's available today is all client hardware. We'll get a lot more EPC up in gigabyte ranges for server, but for now, you effectively have 92 megs as your max. But EPC is really just specialized memory. It has very strict access permissions, but at the end of the day, it's still memory. There's an instruction that is Enclave leaf for writing back a page. There's some other instructions that you have to execute up to this point to do some tracking, but when you actually want to evict it from the EPC out into, for example, RAM, you do this E-write back. That writes the encrypted data out to RAM. It doesn't necessarily have to be RAM. It just has to be accessible memory, so you could have this backed by persistent memory, for example. The other aspect of page out is that the CPU writes an ID to what's called a version array. And this version array is another type of EPC page. And that gives the hardware a way of tracking what pages were actually evicted from this processor so that you can't craft an attack to have a page line in RAM and try and make it look like a page that belongs in the EPC, or by capturing a page that was evicted on some prior reset or from a previous enclave and try and feed that back in. And then there's another structure that resides outside of the EPC called the paging crypto metadata block, and the E-write back instruction also jams some data in here. It's just metadata about the page and about tying it to the version array, so that when you want to bring it back in, all of that, the metadata for the page resides there, so you can correctly verify that, yeah, this is the page for this enclave and its data is intact, et cetera. The other aspect of page out, and this is a pain point for virtualization, is that this SECS, which is a secure enclave control structure, And it's the kind of parent page for all the pages in an enclave. When you create an enclave, the first thing you do is give it this SECS. This holds the base, the size, and we're also ref counting here. SECS children can't be evicted. SECSs with children can't be evicted. And we'll get into that later of why that's a pain point. Page in, we're just reversing. There's an eload instruction. So we're loading back the encrypted data from RAM, pulling data from the crypto metadata, pulling the ID from the version array, check everything out, update the ref count, and we're good to go. The last piece of SGX that's kind of relevant to virtualization is launch control. So there's this whole mechanism, for better or worse, where you need this token to initialize an enclave. A token can only be generated by a special enclave called a launch enclave. And a launch enclave itself doesn't require a token, but it has to be designed by a special key. And on initial hardware, so Skylake, this key was hard-coded to an Intel key. Obviously, this did not go over well with open source community because it meant that Intel basically had to bless all of the enclaves that you wanted to run. So in comes launch control, and this allows you to create enclaves without first having to get whitelisted by Intel. Provides a set of MSRs that you can use to specify your own hash of a public key. So essentially allows you to kind of define your own root of trust. And then it's just a feature that's enumerated via CPU ID. So on that line, the virtualization touchpoints, CPU ID, kind of your standard. Okay, we have to manage all the feature bits. There's an SGX-specific leaf with a bunch of bits enumerating capabilities, what instruction sets are reported, et cetera. And then also subleafs for the EPC sections. MSR perspectives, there's a couple new bits in feature control, and then the aforementioned public key hashes. Virtualization specific or VMX specific, there are controls to intercept the Uncle S leafs. Because they're leaf-based, it's a bitmap field, so you can trap on specific leafs and allow other leafs to execute cleanly. You get a new VM exit reason to handle those intercepts. And then the enclave page cache is the big piece. So we want to expose a virtual EPC region to the guest, manage the physical backing, and do some reclaim and oversubscription. But that has a lot of pitfalls and caveats to it in a VMM world. For Uncle S, intercept the leaves as necessary to inject faults. There's no enable bit for SGX, largely because it has so many different leaves and there are multiple instruction sets depending on your hardware. So if SGX is enabled in the host, to prevent the guest from using it, you can't just toggle a CR4 bit. You have to actively intercept and inject faults. Leafs can be disabled via CPU ID bits, so you have to trap to inject UDs, et cetera. For the most part, we just pass through leafs. There's no reason in base SGX support to intercept any of the SGX1 and SGX2 leaf functions, unless you have launch control enabled in the host. And this is because when you're initting an enclave, you have to have a matching public key hash. Writing the MSRs is extremely slow, even for MSR standards. And einit is even slower. Einit is so slow, and it's actually interruptible. But what this means is that trapping the MSRs and then intercepting einit on behalf of the guest is actually basically unnoticeable from a performance perspective. For the EPC, virtualizing that, it's kind of the same approach as normal RAM. Allocate on fault access. To actually set things up, we have to attach to the VMA to put in our own fault handler because EPC memory is not stored on standard normal memory in the host. So we have to tweak flags, point at the right PFM, allocate the pages from the SGX subsystem. Optionally, we could reserve EPC at VM creation. There's no dependency on the user space driver. So this means that we're only dependent on basically the EPC portions of the SGX subsystem. And this is a deliberate design thing so that you don't have to load that user space facing driver. The user space API, there's basically two options that I've come up with. I've implemented both, playing around with them. One option is to just extend the set user memory region with a new flag to say this is EPC. Requires minimal changes to KVM, kind of fits in nicely. Again, EPC is just really specialized memory. And then alternatively, you could also do a new I/O control. Pros there being that it's easier to extend in the future if you want to do some specific EPC stuff that doesn't necessarily fit well with the existing memory region stuff. Qemu, it's a lot about the CPU ID bits. For time, I'll skip over some of the other stuff. MSRs, expose stuff when you can is the basic concept. Run low on time, so I'll skip past the Qemu stuff. Get into oversubscription real quick. The hardware enforces strict rules about how you do oversubscription, and avoiding conflicts is very painful. And the real big downside is because of all the SECS ref counting and the concurrency rules, conflicts are visible to the guest, and then the ref counting means the VMM can't evict the SECS if it has children that are resident in the EPC, and then vice versa, it can't reload evicted pages. So the big danger there is from the VMM perspective, you evict all the pages, and then the guest manages to evict the SECS from under you. You can't pull back in the rest of the Enclave's pages. So the EPC oversubscription without hardware support is beyond complex, even by SGX standards. So not supported in KVM yet. Down the road, there is hardware support for oversubscription. It's in the SDM now. It adds new leafs to help you either avoid conflicts or to handle them cleanly. Gives VMM some new instructions to manage the virtualization of paging out EPC. And then some new VM exit reasons to handle those conflicts and whatnot. The other thing in the works is an EPC cgroup. Main motivation here is EPC is very limited and it's a shared resource. So for example, a misbehaving or poorly written enclave can basically do a whole denial of service for all of SGX, and also because getting stuff in and out of the EPC is extremely slow. Real quick on that one, it's loosely modeled after, if you're familiar with cgroups, with the version 2 memory cgroups, and just accounts everything. So that's the other piece of virtualization that's in the works. As far as upstreaming, it's been a very bumpy road. I could spend an hour talking about why it's taken so long to get SGX base support upstream. And because of the EPC management, KVM is dependent on that. There's an outside chance it'll make 421, but at this point, that's not looking very likely. So from a KVM perspective, we're waiting on the SGX subsystem. But while we're waiting, I'll be getting some RFCs out very soon, hopefully. I was hoping to get them out before this talk, but that didn't happen. As far as the C group, likely it'll defer until well after KVM bits land upstream. And if you want to play around with things, there's links here for both the Qemu and KVM bits. And the KVM side also has the C group code and the user space driver. I have no idea if we have time for questions. No time for questions. But I'm here all day.